Okay, how do we find vertical and horizontal asymptotes? So vertical asymptotes occur typically whenever the denominator is equal to 0. However, there is a caveat here. All right, the denominator equals 0 and the numerator is not 0. Okay, so if both the numerator and denominator equals 0 at some value for x, then you don't get a vertical asymptote necessarily. In that case, we'll see one in a second. We're going to get a hole in the graph, what we refer to as a removable discontinuity. Now, a horizontal asymptote, where you get close to at the extremes, way off to the left, way off to the right on a graph, these are dependent upon the degrees of the numerator and the degree of the denominator. Three different things that could happen. Denominator could be bigger, in which case you get y equals 0 as your horizontal asymptote. You're getting close to the x-axis at the extremes, way off to the left, way off to the right on a graph. Now, the other thing could happen, the numerator could be bigger. If that's the case, you don't get a horizontal asymptote. And the last thing is they could actually be equal. All right, have the exact same degree numerator and denominator. Now, our definition here saying horizontal asymptote at a ratio of the leading coefficients sounds kind of intimidating. It's really not that bad. So let's jump into a couple examples and see what we're talking about. We're also going to answer some other questions on these, reviewing over domains, x-intercepts, as well as vertical and horizontal asymptotes. So the first thing here is, given a function, we want to think about the domain. All right, the domain, being that it's a rational function, we have a denominator, we don't want to plug in any x values that would make us divide by 0. So this one's factored for us, which is really nice. If it wasn't factored, I would work with the function and try to factor as much as possible from the very beginning. So in this case, we would not want to plug in 1 for that first factor, -2 for that second factor, or +5 for that last factor. Okay, we could put this in interval notation, but let's just leave it like that for right now. All right, next, thinking about vertical asymptotes. Now, if I plugged in a 1, it would make the denominator be 0. Okay, so that's a potential for a vertical asymptote. It would not make this factor equal 0 in the numerator, right? 1 minus 2 is not 0. 1 plus 3 is not 0, so it wouldn't make that factor equal 0. So because it would make the denominator be 0, but not the numerator, that means it also goes as a vertical asymptote. So x equals 1, the vertical line is going to be a vertical asymptote. All right, what about -2? Okay, think it makes the denominator equal 0 for this factor. If I put -2 minus 2, that's -4. That's not 0. -2 plus 3 is not 0 either. So that means that also goes as a vertical asymptote. And then finally 5. 5 makes this factor equal 0 in the denominator. Doesn't make this factor equal 0. 5 minus 2 is not 0. 5 plus 3 is not 0. So it also is a vertical asymptote. So all three of them are vertical asymptotes. The domain question for rational functions and the vertical asymptote question for rational functions is very, very similar. You're kind of looking at the same place, right? The denominator on both of those. All right, x-intercepts. We know x-intercepts occur when y or f of x equals 0. So if I set this whole function equal to 0, like replace the f of x equals 0, my first step in trying to solve this would be I would want to get rid of that denominator, right? I would want to multiply both sides by that denominator because I can't solve for x while it's in the denominator. But let's think, if I multiply that to the other side, it's going to go away. Right? It would go away from the left side because I multiplied by it, and 0 times it on the right-hand side is going to be 0 because 0 times anything is 0. So what's that leave us with? Well, it leaves us with the simple problem that x-intercepts are going to occur whenever the numerator equals 0. So thinking to ourselves, when is that numerator going to equal 0? It's factored, so if I plugged in a +2 for that first factor, it would equal 0. If I plugged in a -3 for that second factor, that would equal 0, and therefore the whole, because they're factors, it would make, when you multiply it by the rest of that side, it would make the whole side equal 0. So both of those go as x-intercepts or zeros or roots. Written as ordered pairs, that would be 2, 0, and -3 is our x value, 0 was our y value that we plugged in. All right, finally, horizontal asymptote on this one. Horizontal asymptote, remember, was dependent upon the degrees. So on this one, because it's been factored, we're going to have to do some visualization that if I multiplied this back out, x times x would give us the highest power of x in the numerator. So that's just going to be an x squared. And in the denominator, we actually have 3 copies of x. If you took the time and multiplied it out, say multiplied these first 2 together, you get an x squared. That x squared gets multiplied by this next x, you get an x cubed. So the degree of the numerator is going to be 2, degree of the denominator is going to be 3. So checking back at our rules here, if the denominator was bigger than the numerator, then we get a horizontal asymptote at y equals 0. Okay, let's try another one. This one has also been factored, but is a little bit different than that previous one. All right, we're going to be looking in the same spots, right? Domain, you still don't want the denominator to be 0. You don't want to divide by 0. So you get x equals -3 for that first factor in the denominator. That second factor is a little bit trickier because of the 2. One way we could do this, and I would encourage you, if you can't visualize it quite all in your head, go ahead and just set it equal to 0 and solve down. So that's going to be an x value of 1/2. We're not allowed to plug in 1/2, and I should be using not equal to signs here for our domain. And the last one, you could set it not equal to 0 and try solving down, or you could just say I'm not allowed to plug in a -6 because -6 plus 6 makes 0. All right, the next question was vertical asymptotes. So our potential candidates here are x equals 3, x equals 1/2, and x equals -6. All right. What you want to do is kind of compare, if I plug this -3 into the numerator for each one of these, would it make any of those equal 0? Well, no. -3 plus or -5 is not 0. -3 plus 6 is not 0. And -3 minus 1 is not 0. So that means that it's okay. That's a vertical asymptote. What about 1/2? Okay, it came from this factor. Well, 1/2 minus 5 is not 0, 1/2 plus 6 is not 0, and 1/2 minus 1 is not 0, so it's a vertical asymptote as well. What about -6 though? Okay, -6, not a problem here. This middle term though, it is kind of a problem, right? -6 plus 6 equals 0. So if I try to evaluate this function at -6 by plugging -6 in for each of our x's, you end up with 0 over 0. So that's a little bit of a problem. So that means it's not a vertical asymptote. However, it can be what we refer to as being removed, right? Same factor, numerator and denominator. We could put this into what we could refer to as lowest terms. Lowest terms would be eliminating that common factor between numerator and denominator. So you get x minus 5 over x minus, or times x minus 1 over x plus 3 times 2x minus 1. All right. If you put it in lowest terms first, then in lowest terms, it's just the denominator that gives us all the vertical asymptotes. But that -6 still isn't in our domain. All right. We're not allowed to plug in a -6. So what's going on there? Well, that -6 actually works out to be where we get a removable discontinuity. All right, what that works out to on a graph is that's a hole in the graph. It's like one missing point in our graph. All right, the rest of the graph looks just like what the graph of what's in lowest terms, that rational function is, except for we get a removable discontinuity at an x value of -6. All right, if we wanted to locate where that actual point is on the graph, where that hole is, where it's missing, what we could do is we could go ahead and fill that value back into the lowest terms. All right, we could evaluate -6 minus 5 times -6 minus 1 over -6 plus 3 times -6, or sorry, 2 times -6 minus 1 more. All right, and that would be exactly where the y value This would be our y value of that ordered pair. So it'd go -6, comma, whatever comes out of that. I'm not going to work that out, and you'll probably not be asked to actually find that ordered pair. All right, next up, X-Intercepts. Hopefully you remember from that previous example, we want to look for the numerator when the numerator would equal 0. All right, so one at a time here, I would say, well, the first factor, x minus 5, is going to be at an x value of 5. What about x plus 6? All right, if I go back here, we had an x plus 6 as one of the factors in the numerator. But am I allowed to plug in a -6? All right, is that going to be an x-intercept? And it turns out it's not, right? It's not in our domain, which said we were not allowed to plug in a -6. So we're not going to get a point at -6, so it's not an x-intercept. If you put this into lowest terms, you can just look at the numerator for the lowest terms version of the same function. And we still have that other factor in the numerator, x minus 1. That's going to go as a positive 1. So we have 5, 0, and 1, 0 written as ordered pairs. All right, last thing, horizontal asymptote. Let's think, what would the degree of the numerator be and the degree of the denominator be? All right, the numerator would have, actually in the original, we end up having 1, 2, 3 copies of x multiplied together. So that ends up being degree 3. The denominator, we had 1, 2, 3 copies of x being multiplied together. So again, that's degree 3. But here's where the visualization really has to take place. When the degrees were the same, it was supposed to be y equals the ratio of leading coefficients. So what does that mean? Well, the leading coefficients for a polynomial were if you took the time and multiplied the whole thing out, the very highest power on x. So to get there, I like thinking this is the highest power in this factor, so x times an x times an x, that's where we got our degree 3, but that leading term would just be x cubed. But let's think about our denominator. Highest power of x, x, times 2x, so that's 2x squared, times another x is 2x cubed. So our leading term would actually be 2x cubed in the denominator. Well, the coefficients there are 1 and 2, the numbers out in front. So our horizontal asymptote is going to be at y equals 1/2. All right, hopefully that makes sense as we're trying to get through rational functions, understand where all these different pieces come from. It takes a little bit of practice to get comfortable with these, but keep going. It's really not that bad, but it does take practice. Good luck.